introduce yourself as I asked, and after this, we begin.
Okay, so thank you very much for the invitation and for the interest in our work.
And welcome to this very special edition of Campus Conversations. We'll be talking with Chancellor Carol Prisk, the Executive Vice Chancellor and Provost.
Okay. I'm Rodrigo M from University of São Paulo. I'm a PhD student here at the University of São Paulo, actually. We are working in a group with many people. The principal investigator of this work is Gabriela Gomes. She just left Liverpool School of Tropical Medicine, and she's now at University of Strathclyde in UK. Yeah, but this cooperation is between many researchers. We have here people from the University of São Paulo, University of Edinburgh, Virginia Tech, National Institute of Health in United States, Instituto Gulbenkian de Ciência in Portugal, University of Porto, and the University of Oxford in UK as well. So I'm here based in São Paulo. I have cooperations with Gabriela Gomes. She is my co-advisor in my PhD studies, and basically we were studying malaria, malaria transmission, and making mathematical models for describing the transmission in the Amazon basin. And now with this COVID, we are trying to apply the same philosophy that we used for the mathematical models for malaria in COVID-19. Okay, so I'm gonna share my screen here and start the presentation. So share screen, and I have this one. So can you just confirm that you are seeing my screen? Yes, okay, great. So let me just put this.
Not yet.
Read more full screen. Not yet? Or yes, I saw.
Yes.
Yes. Yes. Okay.
So then, can I continue? Yeah, okay, so I will continue. So here the title of our work is Individual Variation, Susceptibility or Exposure to SARS-CoV-2 lowers the herd immunity threshold. So as I said, we are going to talk about the dynamics of the disease, and I would like to start without many introductions about what is COVID and this kind of things, because I assume that everybody is involved on it. And then we go to some information that is widely spread into the media, and they are saying, I just selected here two opinions published in the New York Times, and they say, for example, that herd immunity will be achieved when 60% of the population is infected. Also, other epidemiologists are saying the same. Here, even they showed a graph, and this information seems to be accepted all around the world. And I would like to start showing how this is defined and what are the assumptions to say that to reach herd immunity and this being around 60%, what are the assumptions behind the models that underlines this fact? Yeah. So then, okay, starting with a very simple mathematical model, this SIR model. So here we have.
I don't see the next slide. I don't know if the rest do.
I'm stuck on the first slide.
Everybody can see or no? No.
I don't know what the rest is.
Only the first line.
Only the first slide.
On the first slide.
Let's see.
There.
You see?
Yeah.
If I let me see if I change it has changed.
Now, yeah,
okay.
now it's changing. Now it's good.
Okay, perfect. So I keep moving. So we have this very simple model. I think everybody's familiarized with this model. Is an SIR model. We have the compartment of susceptibles, the compartment of infected, and then recovered. So, and susceptible individual will get infected according with the force of infection, and then will recover according with this recovered rate. We see here the dynamics there. We can assume that at the beginning of the epidemics, everybody's susceptible, and then according with the force of infection, this susceptible compartment will decrease, and then the number of infected will increase over time. Here I'm just considering n are not equal to 3. So to have these dynamics here, we have the assumption of an homogeneous population, yeah? With this model and the assumption of an homogeneous population, we can define the R naught. For this case, the value is just the fraction between beta and gamma, where beta is one component of the force of infection, and gamma is the recovered rate. So the R naught is, people are talking about it everywhere right now. So it's the expected number of directly generated cases by one case in when you assume that the population is completely susceptible, yeah? So considering these are not defined previously, we can also define the effective reproduction number. That is the reproduction number occurring instantaneously, yeah? So if the number of susceptible is decreasing over time, so then RT, which is the effective reproduction number, is also decreasing. The RT is defined as R0 times the number of susceptibles in the population. So here I just wrote a very brief definition of this: expected number of cases directly generated by one case considering the current status of the population. Keep moving, we can then define herd immunity, the herd immunity threshold, which is the value of infected people, the cumulative number of infected people when this effective reproduction number is equal to 1. Yeah, so then the herd immunity threshold here, just something, just some definition, the fraction of immune people in a population in which the pathogen cannot spread easily through the population. So if we have RT defined as R0 times the number of susceptibles, and the number of susceptibles in this model, SIR, is the number, is the total number, yes, equal to 1 minus the number of infected, and we want this to be equal to 1, we can just manipulate this formula and see that the herd immunity threshold is equal to 1 minus 1 over R naught. Again, this is for the homogeneous population. Yeah, we can see here in the graph that the herd immunity threshold is reached when we had the maximum value of infected in the population. After this, the number of cases here in the incidence starts to decrease naturally. Yeah. We also can define the epidemic final size, which is the fraction of infected people in the end of the epidemic. Yeah, so here I'm defining this as the cumulative number of infection when T goes to infinity. So here for this case, we can see that the epidemic final size is really close to 1, and the herd immunity threshold is around 70%. So okay, I put here, considering R not equal to 3, and we find the herd immunity threshold equal to 0.67, close to 7%, and the final size, epidemic final size, close to 95% of the population. If we consider a slightly different model, this SEIR model, which just where we just include the compartment of exposed, means pre-symptomatic. Yeah, they did not develop symptoms yet, and they are not observed by the system so far. We have the same behavior for R0, but here we have to take into account the two different parameters, which is delta, the incubation period, and rho, which is the relative infectivity of E with respect to I. Yeah, and all the rest are T, the herd immunity threshold, and the epidemic final size, they are the same. If we consider R not equal to 3, we have the same values as the SIR model. Again, the assumption here is the homogeneous population. And then after putting this, I just want to show, for example, here we have an early release. Here is, they are saying July 2020, yeah, and they have this paper. In this paper, they estimate R naught. I'm not gonna go into the details of the estimation, but then they find R naught equal to 5.7. Yeah, and they keep going in the paper, and the implication for intervention strategies, they say that with R naught equal to 5.7, the herd immunity threshold increased to 80.2%. It means that 80.2% of the population has to be infected to reach a point in which the disease will decline naturally. And we see that this value here, even for this really new article, is based on the formula that I just showed you before. Is the underlying assumption of this is an homogeneous model. And all those ideas are completely spread into the media right now. We can see here in the Guardian, because of that report, they say that the herd immunity threshold may be as high as 85%. So we have a different understanding than this. And I would like to show you what we understand and what we consider into our models to say that individual variation decrease the herd immunity threshold. So then, starting now about the ideas that we have developed in this paper that I'll share with you the link. We consider individual variation. What does it mean? So before, when the assumption is homogeneous population, it means that all the individuals are equal with respect to COVID-19, with respect with susceptibility, with respect with exposure, okay, so let's consider these two characteristics. But we know that there are people that are more connected with others or have higher or lower susceptibility to it. And then we try to integrate this into our model. And when we see here that if we have this individual variation, like more susceptible individuals will become infected first. And then after all these high susceptible or exposed individuals become infected, it's just left a pool of low susceptible or low exposed individuals. And because of this, how is the dynamics of our systems? So, and then now, from now on, the underlying assumption of our model is heterogeneous population. So let's start with the individual variation in susceptibility. Yeah, so we consider this an X factor, yeah, which would be the susceptibility factor. And this is, and then we have a distribution for susceptibility. Yeah, if you, mathematically speaking, if we want to integrate this into our model, we have to consider a force of infection as it is shown here. Yeah, we just integrate over the susceptibility factor, E and I, and also consider the whole factor here, multiply this by beta, and then we have the force of infection. We just plug this force of infection considering the distribution of susceptibility into our model, and then we analyze the model, and then we derive the basic reproduction number considering distribution of susceptibility. Here we have for RT, for the herd immunity threshold and the epidemic final size, we have the same definitions as before. But for the basic reproduction number, if we consider a distribution of susceptibility, it has also to take in consideration the mean susceptibility of the population. These R0 can be derived by the next generation matrix. I just put here a reference if you want to see more details about it. Here, the mean susceptibility factor, we always consider as equal to 1. And then we have this coefficient of variation, which we still don't know, but we use this as a parameter to see how the dynamics evolve, considering different values of variation in the susceptibility distribution. If then we make a simulation, if we consider for the distribution of susceptibility and gamma distribution with R naught equal 3, the mean susceptibility of the population equal to 1, and the coefficient of variation equal to 1, our herd immunity threshold drops down to 0.44, and the epidemic final size to 6–7% of the population. Yeah, this is different than the values we had before, and we have a very big difference. Yeah, it's dropping from 6–7 to 44% of the population. And here we can see the dynamics as well. Yeah, when RT starts decreasing because of the number of susceptibles is decreasing, when it crosses 1, we have the herd immunity threshold, and this is 0.44. And the final size is also reduced, the epidemic final size, from 94 to 6–7%. This variation that we included in the susceptibility distribution, we can simulate a higher one. Yeah, let's see. Let's suppose that we have coefficient of variation equal to 3 and all the other parameters the same. This is decreasing a lot. This is decreasing dramatically. From 6–7%, it is decreasing to 11% of the population. And the final size is 18%. Yeah, if we have this value and this distribution. I have to say as well.
And what's the difference? What is the distribution came from in the same model? The definition of the same model again, where you put the variations. Could you show me that one again?
This one?
No, what is the definition? No, the new one, yeah, the new one, the new SER model. The previous one, how does it change?
I don't know what do you mean, but like the
Right. So at that point, I mean, what is the change in the equation from the previous model? What is the new equation?
So here we have the
here,
new
okay.
equations. Yeah, we just.
Oh, they multiply by x over there.
Yes. We just integrate here the new force of infection that takes into account the people that is infected, and here we have X as well. Basically, this is an infinite dimension systems. We just discretize it in many beings, and then we solve for each being. Yeah, and then so just it's okay. Can I keep moving? Yeah. Okay. So just
sorry, I have a small doubt. Can you go before to the formula? There is no there is the q of x factor is included in the dx, or it's implicitly written there, or is it missing?
Where
in the formula you just showed me.
The dynamics.
This formula.
Here, yeah, the Q is in the D.
Q is implicitly included in the dx.
So
right.
Q is the distribution of X.
Yeah, but in this integral expression, you didn't include Q of X.
Yeah, we don't include here. We just we have a distribution of X, and then we discretize it in many bins. This is just the numerical solution. Yeah, but we don't have to consider like Q into this formula. We just consider the X, and the X, the composition of all the X, all the susceptibility of the population is drawn by a distribution, and this distribution is what we are considering a gamma distribution.
I suppose that in fact he considered only the sample, a sample for each X. I suppose.
Yes. Okay, just moving forward. Oops. Okay, we were here. So it is then, if we consider a coefficient of variation 3, it drops down to 11%, and the final size 18%. Yeah. So the second case here.
No, sorry, but I'm a little bit puzzled. Can you go before? Sorry.
Just tell me which one.
In the formula of lambda here, in this formula, you shouldn't weight the different values by Q in the integral there.
In the integral here.
No, he's adding all the.
Like here is just lambda. So if we have an homogeneous model, how do? We have just beta, and this is the sum of E plus rho, I plus rho E, right?
No. If you have a homogeneous, this would go out from the integral, and you would have infinity. You need to have a weight for the integral to be finite.
No, the I and the E become very small, I presume.
Yeah, the I and E, we are considering just a population from 0 to 1. And if you integrate over infinite, the maximum value you get for each of them is 1, because we have a distribution of Q.
So do we get it right that the Q shows up in the initial condition for S?
Yes, yes.
Like going back to the previous slide, that the one that defines the model, like
Here.
that one is missing the Q. I guess that's. So is that the initial condition for S?
In the initial condition, we consider amount of people in each category of X, yeah? And this is given by Q, the distribution of susceptibility into the population.
Susceptibility, okay.
Yeah.
Okay,
So,
okay. I got now. I understood.
yes.
Okay, yeah.
Okay, so moving forward. So then the second case. The second case, so we consider this individual variation as exposure, and then we assume that exposure is we can correlate exposure with connectivity. Yeah, if you have if you have many contacts, you are more exposed to get infected, and then we assume a positive correlation to infectivity as well. So if you have many contacts, you have higher chance to get infected, but you also have higher chance to infect other people. And then mathematically speaking, to translate this into our model, our force of infection takes this form, which also consider X here in the formula for the force of infection. Yeah. If we apply this into our model, we have the same, but with different force of infection. And then if we compute the R0, in this case, the R0 takes into account also the second moment of the distribution, which is the variance of exposure. We don't know the value of the coefficient of variation, and then we use this as a parameter to apply in the model. So here, if you have a gamma distribution, R0 equal to 3, and the coefficient of variation 1, so from 6.7, now we have 33% for herd immunity threshold. And the epidemic final size is 54. If we consider the coefficient of variation equal to 3, we have much lower values, 6% for the herd immunity threshold, and the epidemic final size 11%. Of course, all these that I showed you so far is just an epidemic-free dynamics. We are not considering any kind of interventions, and in real life, we have all the governments are taking measures and applying social distance and all those things. So then to simulate this, we just consider that it takes 14 days until the maximum effectiveness of social distance measures is reached once is introduced in the country. The maximum lockdown, I'm just here like lockdown, but maybe it's not lockdown, but the maximum efficacy lasts for 30 days, and the control measures are released slowly during half year. We consider that this implementation is linear. Yeah. So then considering here a reporting rate of 6% of the case, then delta equal to 1/4, gamma the same, and whole equal to 0.5. And fitting R0 and the maximum lockdown efficacy, I just got data from one country in Europe, considering that the purpose of this presentation is not to talk about a specific country. I think it's not important to know which country this is. So then we fit the data. We have these dots here. The dots are the data, and then here is our model. But here we are considering an homogeneous model. If you consider an homogeneous model, so after this, we're going to have a huge second wave, because the underlying assumption, an homogeneous model considers that you have to reach 6-7% of the population infected to have herd immunity. So if we simulate this, we are going to have something like this, yeah, for the homogeneous model. If here I just want to compare the epidemic without intervention with intervention. We can see that the intervention is also reducing the epidemic final size. Yeah, it's reducing from 94 to something below than 94. And then if we use an heterogeneous model with the coefficient of variation equal to 1, we are going to have, our model predicts that we are going to have a much lower second wave. Yeah, much lower second wave. Here we have, I didn't say in the previous slide, but here we have R naught, and then they implement the social distance measures. It takes 14 days until it reaches the maximum efficacy. It stays in the maximum efficacy for 30 days, and then it's linearly coming back to normality, and this takes half a year. And then if you calculate the effective reproduction number here, we have this value. As soon as you are releasing the social distance, the effective reproduction number will cross 1. When it crosses 1, or when it's bigger than 1, then you trigger the second wave, and then it increases until you have this shape. But if you consider a coefficient of variation, just saying here that with social distance measure, you have a lower epidemic final size. But if you consider the coefficient of variation equal to 3, you have a much different scenario. So it means that if you consider that your population is much more heterogeneous, you have a completely different scenario than the homogeneous model predicts. And this, just emphasizing this, all these 6-7% that we see on the media, or between 60 and 70% for the herd immunity threshold, assumes that the population is homogeneous. And then here with CV equal 3, we have a much different scenario. Yeah, just comparing again. Now, if we consider, instead of the distribution, instead of the heterogeneity, instead of being in susceptibility, but is in exposure or connectivity, we have this scenario for CV equal to 1, and for this country, if CV is equal to 3, this country is done. Yeah, there is no second wave for this country, which is completely different predictions than if you consider your model or your population homogeneous. So then here we just draw all the values for the herd immunity threshold, which is this line, and the epidemic final size, which are these lines, these both lines. The black one means variation in susceptibility. The gray one means variation in connectivity. If we increase the coefficient of variation, the herd immunity drops down considerably. And so we don't know the value for CV in this case, but many diseases are around those values. For example, we calculate this for malaria in the Amazon base is 1.8. In Africa is 2.4. Tuberculosis in Portugal is 2.4. In Brazil, 3.3. And so we still don't know, but there is, at least we we think that this should be around those values, but for sure we still don't know this. But here, as all the values that I just presented to you before, we are assuming a gamma distribution. We also don't know if this can be drawn by a gamma distribution, the distribution of variation. If we change this distribution, if you consider a log normal distribution, for example, we have the shape is more or less the same. It's increasing a bit in comparison with the gamma distribution. Yeah. So, but we don't change our conclusions. They would be the same as the coefficient of variation increase, the herd immunity and the herd immunity threshold and the epidemic final size is also decreasing. Here I just want to show you, like, we have this is the status right now in the world, like shame on Brazil, but let's focus on the countries here in Europe. So this is log scale. The number of new cases are decreasing dramatically in comparison with the peak of the epidemic. Yeah. So right now, or in some time, we'll be able to know for sure what is the coefficient of variation in this case, because if the epidemic vanishes, yeah, and one explanation, if we don't have a vaccine yet, and if the social measures are relaxed and the epidemic is not coming back, the plausible explanation would be herd immunity, and then we will be able to have higher confidence to say which value we have. Just some points that I would like to emphasize here. Our result depends on we have to consider that once one is infected, this person will be immune to the disease for several months. If it's not like this, then our model fails. Yeah, but it seems so far that this is not a bad assumption. Yeah, we saw that herd immunity threshold and also the epidemic final size is declining sharply when the coefficient of variation increase. But we are still in the middle of the pandemic. We don't know many things, and due to all these uncertainties, serological surveys would be a tool for understanding what is the current status of your pandemic, and especially if you want to relax your social measures. Yeah, you have to follow up and see if if the number of cases or the prevalence of serology positivity is increasing or not. Just with this, you cannot be supported just by models to make all your decisions. You have to follow this with real data. Our further work, like what we are working right now, we are trying to estimate CVs for countries where we have better informations. And yeah, as soon as we have this, we are gonna update our work online. Spain, I think many of you saw this already. Spain is doing this. Yeah, Spain is relaxing the social distance measures and is following up with serological surveys. We can see here that in the beginning of May, Spain had an average of 5% positivity in the serology study. After 1 month, in the segunda ronda, yeah, in the second month, here in the beginning of June, end of May or beginning of June, Spain had just 5.2% of positivity, which means that they can be more confident in relaxing the social measures. They are not just based on models. If they were based on models like homogeneous models, they would not open, but they are following this with serology tests. There is another study that is online from Tom Britton and colleagues that also saw that herd immunity is decreasing with the increase of heterogeneity in the population. It was up just after days of our model, and yeah, they used different strategies, but they saw the same, that the herd immunity threshold is declining with the increasing in the heterogeneity of the population. Here, I just have to acknowledge, Gabriela Gomes is the principal investigator of this work. All our colleagues that are working in this project, we stopped our life just to do this for many, many weeks, and now maybe we are reaching the end. So with that, I would like to thank you and leave this, it's not the link here, but you can easily find it on medRxiv. If you want more details, we have, we are also fitting different countries in the supplementary material of our work that is already in medRxiv. Thank you. Thank you.
Very good. Okay, so perhaps you we open to questions. You can either ask in the chat or simply ask the questions if you have them.
So I have a question.
Please.
So how do you estimate this CV? You know, you're saying you're doing that in other countries.
Yeah, so yeah, basically we are trying to infer the CV based on fitting. Yeah, we are making different fittings and considering this CV also as a parameter and using Monte Carlo, using different methods, and try to infer this value. Of course, this is not a simple idea, but there are some papers also trying to estimate this variation among other disease or other populations, and then the final message is that we are trying to infer by fitting. And yeah, so I don't want to anticipate anything, but it's not going to be surprising. Very likely we have values similar with the other disease.
So that's the way you calculated the ones for the other diseases, or that they are calculated, the CVs by fitting with the same model?
Yes, yes. In our work in medRxiv, you can find all the references for all the countries. Maybe I can move here. So we have all this, yeah, from malaria, Portugal, tuberculosis, SARS-CoV-1. You can see there the way we do.
Mm-hmm. Thanks.
All the reference. Okay, thank you for the question.
So this completely puts down all the herd immunity thoughts.
Yeah, so we are working, especially Gabriela Gomes. Yeah, Gabriela Gomes is working this for maybe I can say decades. Yeah, I think it's around 20 years. She's working in variation or heterogeneous populations and mathematical models. And when we saw all this information into the media, so the underlying assumption of this is homogeneous models. But like sometimes this assumption is does not give you a proper estimate in some cases. In some other cases, you can use an homogeneous model to derive some conclusions. But considering the importance of this disease to the world, we saw here that, okay, we can apply our techniques that we are applying different disease to see what we have. And we had this very shining conclusion, let's say. Yeah, it's dropping completely. And then the countries we already saw in Europe, yeah, many countries are easing the social measures and the number of cases are not exploding again. Yeah, of course, this should be done, as I said, very carefully, especially with serological tests. But what is the explanation if you think about an homogeneous population to not have a second huge wave?
And the comment is that I think that you never return to the 3. You ease measures, but you return to 1.5 or somewhere because you are aware of the infection. And the problem is that in the beginning, people were not aware. So
yes.
Yeah, but perhaps a model with a different return would be more close to what is happening.
Yeah,
not
but
to return to previous value, but some intermediate.
So like, and with this homogeneous value, homogeneous model here, you are still seeing my screen, right?
Yeah.
Yes.
Yeah. Okay. So here it's slowly coming back, and we see the effective reproduction number is also slowly coming back, but with these very low values above 1, we already have this huge second wave. Yeah. Even if it's an homogeneous model.
Yes, I understood. But what I say is that this final value 3 does not seem to be the real value, because we are going to be around 2, let us say, or 1.5, because we know that the disease is there.
Yeah, so let's just look at this here. After this point, the R is already below 1. And here we are around, let's say, a little above 2. And this is already exploding.
But what it could be is that in those places in Europe, the blue line hasn't gone above 1 yet, because everybody's still wearing masks, everybody's still taking care. So we're not in that part yet. We're in the part where the R went up a little bit, but probably not above 1 or just above 1.
Yeah, I agree. I'm not claiming that that what we are saying is the truth. Yeah, but it's some hypothesis that has to be considered into the understanding of the dynamics.
Okay, we have some other questions. Yes, I think that well, I keep the list. It's Chichi that have a question, and then Nicolas.
Well, a little question. Why do you choose the gamma distribution as the good distribution in this model? Only this.
Okay, so the gamma distribution is a very you can manipulate a lot the gamma distribution. Yeah, you can have something close to a normal distribution, or something close to a log normal distribution, or even different than those ones. with a gamma distribution and controlling the parameter that for us is the coefficient of variation, we can take many possibilities, yeah. And then because of this this flexibility of gamma distribution, we decided to consider this one. But as I showed you, if we use a log normal distribution, we have something, we would draw the same conclusion, not that the effect wouldn't be that strong, but still very strong.
Thank you.
Thank you for your question.
Nicolas, go ahead.
Okay, first of all, I agree with the question with Ernesto. There is no reason to suppose that in European countries you will go to R equal 3 in a near future, because there are many interventions, not only mobility stuff. There are. Okay, but this is I have a more precise question. Can I understand your result in the following way, in a simple way? There is only a proportion of the population which has an effective R above 1, and most of the population have an effective R below 1. So only the proportion of the population that have an R above 1 can spread the COVID illness, and the rest doesn't push in favor of that. This is the correct interpretation.
I wouldn't look like this. I wouldn't say I wouldn't put in these words. Like I would say that we have the distribution of susceptibility or exposure, and then part of the population has high risk, yeah, or high susceptibility, and another part of the population has low risk. The ones that has low risk has lower chance to get infected, but they are for the system is just one, yeah, it's just one are not for the whole system. But what varies is the susceptibility of the population, and then this is drawn by the susceptibility distribution, and it is more heterogeneous if the coefficient of variation is higher, is lower if the coefficient of variation is lower.
More questions?
Let me add to
Yes.
what Nicolas was saying. Maybe I'm thinking what you're saying is more that there are a few people that kind of drive the R up, those that are very susceptible.
Yes,
and
yes.
majority put the R like below 1. They are not because how much they're contagious, but how much they absorb it.
Yes, I think these words are more careful. Yeah, because like R is just one R for the whole systems, but each individual contributes with their susceptibility to the composition of this main value or unique value for the whole system.
Okay, Fernando?
Yeah, I had a different question, but just to comment on the previous discussion, it seems to me that your R3 is the mean, so there's a lot of people above 1 there, not just the. So if you're saying the heterogeneity itself helps, it's not clear to me intuitively why that happens, but I have to read the paper and think about it. It's not that a small fraction is not above 1. Most people would be above 1 if the mean is 3. But anyway, going back to my question, the example from Spain that you were discussing, if I read correctly, the prevalence was at 5%. It didn't change from May to June. And are you basically saying that that would be below already the herd immunity threshold in that case? Or was that the implication?
Yeah. So I think we should be really careful to say something like this. Yeah. what I can say is that like you are easing the social distance and then keep measuring the serology of your population. They had 5.0 after 1 month, 5.2. This 5.2 is inside the confidence interval of 5.0 in the previous month. So it means that it hasn't changed. If you keep doing this until you ease all your measures and it's not increasing anymore, yes, then you reached the herd immunity. But saying that you already hit herd immunity, it would just like have political implications that are not careful enough.
Okay, so more questions or comments? We have a lot of people from, I think, Brazil or somewhere that, of course, can participate also in the debate.
Just one comment. I share the Zoom ID with my colleagues from my lab. Yeah, okay.
We are very happy of having you and your colleagues here. This is for us a big moment. Okay. A very big moment. And the results, of course, are puzzling and very interesting to think about. Okay. This is undoubtedly, I think. Okay, so if our colleagues, you can, você pode também perguntar em português, se você prefere. Hola. But if not, then we give freedom to Rodrigo. I do not know how to proceed. Usually, Rodrigo, this seminar and colleagues is the usual probability and statistics seminar that we had at university, but some of us enter into the government advising committee, and other colleagues enter in the university special team for COVID studies. So we decided to move this seminar into the mathematics and quantitative questions of COVID and also social questions. So after this, there is also a discussion of what is happening and so on, but this is the second part. You can take part or not, but I insist if there are no more questions about the very interesting talk that we had.
I have another question. Thinking of what Fernando said. So in the, I guess you guys know the gamma distribution better. So in the gamma distribution, if the average is 3 or whatever, 2.5, and this CV is what, 1 or 2 in your example, like, is it all like majority is still very close to 0 and then it has a very long tail?
No.
Not really.
Like, if you have the mean equal to 3, I'm not sure if it's something like this, but if you have the mean equal to 1, and then you have the coefficient of variation close to 3, you have a very sharp decline. Yeah. So then it's not something like a normal or log normal distribution. Then you have something like this, which means that just a few number of people will have really high susceptibility, and the majority will have low susceptibility.
Majority will have low, right? So the median is much lower than the mean, no? In the gamma, it's way lower, no? Or
no, you have 2 parameters in a gamma.
Right. Yeah.
So you can do whatever you want.
When the variance is large, the median is much lower than the.
Yeah, you can control both. Yeah, you can control the mean and the variance for the gamma distribution.
Or the other way around, when the variance is low. Okay, you got it. Okay, yeah. Thanks.
Yes, in the simplest case, Antonio, you can think at a sum of independent exponential distributions when the parameter is an integer.
Mm-hmm. And let me, Rodrigo, ask a question. Can't you think about, because you think about heterogeneity, but thinking of simple, we take one people and think this is more and this is less and so on, but can you think about geography of the place or some connectivity like these graphs that are small world graphs or something like this?
Yeah,
sorry, perhaps that the classical model is the complete graph that has the N2 connections, but in fact, it is different.
Yeah, indeed, you can consider different scenarios where you can introduce this heterogeneity. Yeah, we tried here to use the simplest model that we could use, just to show the concept and try to reduce as maximum as possible the uncertainty about other parameters. We can see around like huge models that include many things, and each parameter that you include also uncertainty. Yeah, we here are just saying force of infection, recovery rate, and the distribution of heterogeneity. If you want to include this into a map or into different strategies, yes, definitely you can do, and I would say you would have more reliable values, but you also have to consider if making the system more complex, introducing it, will bring you advantage with comparison with an homogeneous in this case.
No, undoubtedly. I think the approach is breakthrough. I mean, I couldn't say convinced because I have to think, but I'm very puzzled by your.
Yeah, it had a very good acceptance in the community. I don't, if you check the link in medRxiv, it was hugely shared, and many people were commenting on that.
Oh yes, because the results.
People wanted to be correct, right?
Yeah. with all this bad news that we have in this period, when comes a good news, yeah, so it would be nice.
Rodrigo, maybe for the case of Spain, if you try to estimate the RT now, in what position of your curve you will be? I mean, the RT now is 1.2, 1.3, and maybe you are not on the peak.
So definitely is not on the peak anymore. Yeah. So
yes.
Like, let me show you this graph again.
Mm-hmm.
Yeah. So Spain is one of these countries. The name is behind Germany or something like that. So it's already declining. If it's declining, the RT, or the effective number, is below
less
1.
than 1.
Yes. But we don't know if the social measures were that strong. Like in Spain, they were really stricted with social distance. Yeah, even like people could not go out without permission, and all those things. I think you guys know better than me the condition in Spain. Maybe it's below 1 because of the social measures, but as soon as it is releasing and it's not coming back, it's not increasing the incidence case, then I would say, yeah, they are below 1, but this should be taken really carefully.
No, I think that there is another effect, the effect of tracking and the new infected cases and its contact is I don't know, the dynamic of the epidemics.
Yeah,
and
so
the SAIR does not take in account this effect.
These would, so let me move again here for an simulation. So
yes.
Here, so let's say the normal are not for the country, it's around 4 here. And then you push it down with the control measures. Maybe the control measures in Spain, considering all the things that they were doing there, are pushing this really below 1. Yeah, it should be understood as well. And this is going to be clear as soon as they start releasing this kind of measures.
I agree. Okay, thank you.
Okay, so I think no more questions then. Yeah, okay, so then I will leave you guys. I will not follow your meeting now. I don't want to be intrusive in this. And I thank you very much for the interest in our work. And yeah, we can share thoughts by email or something like this. I'll be happy to answer if you have further questions later on. Thank you very much.
Thank you, Rodrigo. Very interesting.
Thank you.
Thanks.
Very
Thank
interesting.
you.
Bro.
Chao, chao.
Chao.
Oh.
Bueno, ahora tenemos segundo tiempo.
Segundo tiempo. Ese no es el tercer tiempo.